All right, so this is like, I call it more characteristic classes. So we call what we did so far. I believe we worked with the complex vector bundle. So for complex vector bundles, we define the Chern character of E. This belongs to H even the ROM of M, which is direct sums of H2K, the ROM of M. Okay, this was the Chern character. We have some properties. We call, and we have the Chern classes. This was belonging to H2I, say the ROM of M. So these are Chern classes. Now these guys are actually our integral classes. These guys are rational classes only. You cannot do better than rational. And by integral classes, I mean that if you integrate like this Chern class over some submanifold of dimension, closed submanifold of dimension 2i, for example, you get an integer. Right? And if you integrate this over any closed submanifold of any dimension, you get a rational number. You don't get necessarily integer all the time. Okay? So this is the difference between the two. Of course, I did not prove this. I didn't prove that either. These are, you need another approach to characteristic classes to see this, but that's just to be aware of. We also define Todd genus. Todd genus. So my notation was Todd of E. So this was defined as, you remember, determinant of, so let me write it like this, e to the, I would say minus r, yes, over 2 pi I divided by e to the minus r divided by 2 pi I minus 1, right? Yeah. So here this function, so again, this is something which belongs to H even. So this function is a very interesting function, e to the x over e to the x minus 1. This is one of the exercises. This is sum dm over m factorial x to the n bigger than 0. So this function is the exponential generating function for Bernoulli numbers, right? And Bernoulli number, which is a number which is very important in many places, in topology, in combinatorics, in geometry, in a lot of different places. These numbers appear somehow strangely. It's always through this function, so the two are more or less replaceable. Okay, so that's that. So today's menu now. We want to look at characteristic classes for real vector bundles. For real vector bundles. So real vector bundles are kind of more peculiar and they have more symmetry in some sense. We're going to use that. So I need some general definition, which is the following. Definition. So let me write here. Let E to M be a real vector bundle. Actually, for this definition, you can just use real or complex. So let me put it like this: real, respectively complex vector bundle equipped with a Euclidean respectively Hermitian in a complex case. I mean, inner product. So this is your vector bundle. Each fiber is in the real case, is a real vector space. Then there exists an inner product in this fiber over X, and as you move the fibers along M, this inner product changes in a smooth way, and that's very easy to formulate. So you just take locally a smooth section, and so inner product should be smooth. Or in the complex case, it's a complex vector space, and you take a Hermitian. So Hermitians, you know, are ciscilinear. They are linear in one variable, antilinear in the other one, but otherwise they're positive definite. Right? So that's the idea. Okay, so this is a connection on E it's called compatible. So I can write here still is called compatible with this inner product here if. So there is a very important condition for any two sections S1, S2 sections of E. We have D of S1, S2. You see, you multiply them fiber-wise, take the inner product, in other words, fiber-wise. You get a function, you differentiate it, you get the one form. Okay, so now we are saying this is equal to nabla S1 inner product with S2 plus S1 inner product with S2. So I have to define what do I mean by this right-hand side, because connection takes values. Remember, this connection in our newest definition was a map from C infinity of E going to one forms on M tensor C infinity of E again, and remember this is a tensor product over C infinity of M. These are modules over M, C infinity of M. Okay, and now I have an object like nabla S1 here in this big space, and I'm taking its inner product with S2. So, I mean, so what does this mean? Well, that's very easy to define, right? Because what you can do, you can just say I mean, take an element like there, like omega tensor C1, and you just say C2, for example. You just declare this to be equal to omega inner product of C1, C2. I mean, after all, this is a function, this is a one form, this is a one form, one n, right? So this belongs to omega 1. So you can do the same for the right-hand side. So after all, then you land in one forms, and here you're landing in one forms, and we want this to be true. This is compatibility. So now a lemma that we need is the following. Any inner product, so for any E, and so we can just say a vector bundle equipped with an inner product, either Euclidean or Hermitian, there exists a compatible connection. Okay, so there always exists a compatible connection if you start with a kind of sort of inner product vector bundle like that. So the proof of this again is using partition of unity. Let me write it down. So we just cover M. M equal to union U alphas over alpha, such that this bundle over each U alpha is trivial. That's possible. Yes. Yeah. That's possible by the definition of a vector bundle. And over each U alpha, we choose a frame for, so choose frame. So E alpha I, say I equal to 1 to n, but n is equal to rank of E for E restricted to U alpha. Now, so far, this is a general definition of vector bundle. I haven't used this inner product yet. Now I'm claiming that I can choose a frame in such a way that it's actually orthonormal. Can choose EI alpha to be orthonormal. How can you prove such a thing? Because the general definition tells me that there exists a frame only, which means it's linearly independent at each point over this open set U, right? How can we make sure this is orthonormal at each point? How do you change? Yeah, maybe there's an answer, I don't know.
There's some Schmidt process, something.
Gram-Schmidt, yes, exactly. That's what we do. How did you turn indeed a general linearly independent set of vectors into orthonormal if you have an inner product on your space? Gram-Schmidt. And the Gram-Schmidt is such that if you think about it, it's a smooth process. I mean, formulas, everything is smooth. So you just have to think a little bit. It's not totally clear, but you have to make sure that you understand the problem, and then the solution is just there. I mean, everything. So can choose this to be orthonormal using, I just write Gram-Schmidt process. I'm not sure I wrote the Schmidt rightly, and Gram, I'm not sure if there's two M's or not. Sorry, Gram-Schmidt process. Okay, so using that Gram-Schmidt process, we can pick this to be orthonormal. Now let us define a connection on U alpha So first of all, I declare these things to be flat. I just say nabla alpha of E I alpha to be equal to 0 for all I. So these are flat sections. So this orthonormal frame, I declare them to be flat section. I mean, so far we can do, right? And then what is the general definition for a general section now? I mean, this is the definition of flat. I mean, I'm not saying there's something deep here. This is just a definition of flat, means it's 0. So in general then, for any S, you can write it as sum Fi Ei alpha over I, S belonging to C infinity of E restricted to U alpha. So I can tell you what is the value of my connection on this. This is just sum EFI tensor E alpha I over I from 1 to. Right? I mean, then you check that this is a connection, and you already know that it's a connection. I mean, if this was not 0, you could have chosen arbitrary one forms. That's okay, and this is still would be a connection, but that's not what we want. We want them to be flat. That's important. Okay, now claim is that. So now, well, what we do? Pick a partition of unity. For the cover, U alpha for n. So these are, in other words, F maybe phi, I don't know, phi alpha from U alpha to R. These are smooth functions. I mean, or even non-zero, you can choose a smooth. And such that sum, oh, actually not from U alpha, sorry, from M. Oh my God, from M. Smooth such that sum of phi alpha is equal to 1. I mean, you make sure that the cover is locally finite, so this always exists then over the second countable, some spaces over alpha is equal to 1. Okay, now as we did, you can just define your connection to be sum of phi alpha nabla alpha, right? My notation is nabla. Oh. Okay, now this is a connection on E now, which is defined for all sections, not just sections that are defined on this small part. And now the only thing that remains is to check that this is compatible. So let us check that. Compatibility is a local property. So it's enough I check nabla alpha is compatible connection on U alpha. So suffices to check nabla alpha on U alpha. Okay, pick two sections, in other words. So pick sections S1, S2. So S1, I can write it as sum, say Fi, E alpha I. And S2, I can write it as sum G, J, E alpha J. Right? Now, first of all, what is inner product of S1? S2, this is just, if you go through this is sum Fi Gj, because these guys are orthonormal. Since E alpha I is orthonormal, so you get rid of those nuisance cross terms here, right? It's orthonormal. So if you compute d of this guy, and you can just apply Leibniz to this. This is d of I gi plus I times dgi, right? Over I. Okay, so this is one side of the compatibility. Now you compute what is nabla of S1 and S2, for example. Well, nabla of S1 is nabla of this guy, right? And this guy, we know what it is. This is d of I, sum of d of I. I mean, tensor E alpha I, right? And then we want to do some Gj E alpha j, right? We want to take this inner product. And the inner product, we know by definition how to take it. We just multiply these two things, and then this is just 1, and the other ones are just 0. So this becomes sum Gj, I mean Gi, let me put it like this, d of I over I. The other thing S1 nabla S2 is just again some, okay, just I don't write, this is on the right hand side, and you just get the same thing in this form. You get I dg I. So if you compare these two terms, you get that you're so this plus that is equal to this. So the lesson is that for any inner product vector bundle or metrized vector bundle, there is always a compatible connection for that. Now, we are not saying there is a unique compatible connection. There could be many, many, right? And there is only one case where we know existence and uniqueness both, and that's for Levi-Civita connection, where, so let me just make a note here, because it's something that we already discussed a little bit. Note for E equal to Tn, the tangent bundle, and inner product to be just then any inner product is nothing but what? What was the name of an inner product on a real tangent bundle of manifolds? Do you remember that name?
Dot product.
What's that?
Dot product.
We had more specific name. We are over a manifold now. Yeah, this was at each tangent bundle, there is a dot product, yes. But in terms of geometry over manifold, what this structure is called?
So Riemannian metric.
It's a Riemannian metric, exactly. Yeah, many of you have that, right? This is a Riemannian metric. Okay, excellent. So there is a theorem, the Levi-Civita theorem. It said that there exists unique, compatible, and this and is also important, torsion-free connection. On T. This is a famous Levi-Civita connection that if you have a Riemannian metric, there exists a unique compatible and torsion-free connection. So both conditions are needed, compatibility and torsion-free. This is, in that case, then there exists unique. So this is very nice. When you have uniqueness, of course, it's very nice. But if you drop this torsion-free compatible, there are many compatible, and we construct them even more general than vector bundles. So this is for arbitrary, more general than tangent bundles for arbitrary real and complex vector bundles. So, okay, so then you may wonder if you can take this Levi-Civita theorem and find an analog of Levi-Civita theorem for vector bundles. Maybe we can prove a theorem that says there exists a unique torsion-free compatible connection for this theorem. The problem is you cannot define torsion on arbitrary vector bundles. This tangent bundle is very cherished, very special, privileged bundle. It allows you to do things that general vector bundles don't lend themselves to be operated on like this. So, I just make another note. No notion of torsion. I mean, you have to think about it, but I just write it because I want to put it in this more general context now. No notion of torsion for general vector bundles. Okay, so this was a side remark. All right. So now we have, now that we have this, we can go on and study the curvature tensor of a compatible connection. So the curvature tensor or sometimes we can say operator, it doesn't matter, of a compatible connection. So locally, if you go to an orthonormal frame, in an orthonormal frame, locally in an orthonormal frame, we saw that this operator R is really like a matrix, is an n by n matrix of two forms, right? We got two that is on this open set. There is this matrix of two forms. Now, I claim that if the connection is compatible, if nabla is compatible, then this guy R is a skew symmetric. So this is important in the sense that R plus R transpose equal to 0. In other words, it means that omega ij plus omega ji. I mean, this is the real case, okay? Omega ij, omega ji equal to 0. So in particular, elements of the main diagonal are 0. You just get 0 forms on the main diagonal and off diagonal. So this is very important observation. Now, how you can prove this, that's very easy to prove. You can just use the formula for R. Proof. Use the formula. We had this formula that R was equal to dA plus A wedge A. This A was this connection matrix. Now this A, so show that So here is an exercise that's good to do this. So show A is skew symmetric. Hence, use R is skew symmetric. Just give you a hint for this skew symmetry. You can just start looking at differentiate this relation. I mean, in local coordinates. So 0. Okay. So this is equal to delta J is equal to that. Differentiate this. So now this is equal to, by the compatibility, this is equal to nabla di dj plus okay, plus di nabla dj. I don't even have to go to an orthonormal basis. Okay, so I don't. Yeah, why don't I leave it to you to think about it, because there's a little bit of. Yeah, I have to. Okay, so let's discuss this over the break. Okay. So this is the exercise. So that's so this is important. This is in the case of real vector bundles. For complex vector bundles, this matrix is skew Hermitian. Okay, R is skew Hermitian. By skew Hermitian, I mean, of course, as usual, R plus R star is equal to 0. R star is equal to R complex conjugate transpose. It's conjugate transpose. So in this case, it follows that elements doesn't follow that elements on the main thing is 0. It just follows that they are real on the main diagonal. They are real. It doesn't follow that they are 0. Okay. Is it real or complex conjugate? No, I mean pure imaginary. Oh, they're real. Yes. Oh, sorry. No. Pure imaginary, right? Yeah, because this is plus. So I was confusing it with Hermitian. They are skew Hermitian. So on the main diagonal, in this case, they are pure imaginary. Okay, so we are going to use these two things now to define Pontryagin classes and these things. Are there any questions, by the way? Okay. So let me now continue. So this is the kind of preparatory stuff I need. So now let me define Pontryagin classes. So Pontryagin. Okay, so now let E over M be a real vector function. So this is important. We assume this is real. So I can define this Pontryagin class to be classes. I mean, characteristic classes Pi of E, which belongs to H Durand for I of M, I for I of M are defined by this equation that P of E. So let me put it like this. Actually, I don't need to define this. So determinant of 1 plus R over 2 pi equal to 1 plus P1 of E plus P2 of E plus P3 of E, so on. So notice that this is very much like in the spirit of and total Pontryagin class is denoted by P of E, which is just this some of this thing is just determinant of 1 plus R over 2 pi, right? Now, so remember, recall that this is very much similar to our definition of total Chern class. So let me write it here, compare with definition of total Chern class. Remember, we define C of E to be determinant of 1 minus R over 2 pi I for a complex vector bundle, right? The complex vector bundle. And then we declare this to be 1 plus C1E plus C2E plus C3E. And I says CIE belongs to H2I, the realm of M. So now you have to scratch your head a little bit and ask yourself what is going on. Okay, a priori, if you have this determinant, imagine this is like matrix of 2 forms locally, and you take this determinant, you expand it, you get sums of even forms. But somehow forms of degree 2 and degree 6, degrees that are not even numbers that are not multiples of 4 are missing here from this list. So here there is no form of degree 2 times 2m plus 1. In other words, all forms that appear here, they should be multiple of 4. And we know that there shouldn't be any odd forms because this just consists of even forms. So when you multiply, you get even forms again. But why on earth there are no, for example, forms of degree 2? But here there are. You have this. This is the first Chern class. Form of degree 4, but there is form of degree 6, but there is nothing here. It's just form of degree 4 Starts with 4, then goes to 8, then goes to 12, and so on. So what's going on, right? That's what we have to settle with. I mean, the reason for this is what we discussed. Yes? Question? Okay. So the reason is that, as we discussed, this R can choose compatible connections. That's, I mean, I did not prove this theorem yet, which is the first thing you have to prove, but I prefer to prove. But we have freedom in choosing the connection in order to compute this, this R, right? So you can choose a compatible connection. Then, for compatible connection, R is a symmetric, right? R transpose is equal to minus R. So what can you do using this symmetry of the problem? Then you can say this determinant of 1 plus R over 2 pi. Of course, determinant of a matrix is equal to determinant of its transpose. This fact is universal. This is true over any commutative ring. 2 pi transpose. So this is determinant of 1. Now R transpose is minus R, 1 minus R over 2 pi. From here, you can conclude that actually forms that are of degree 2, 6, and so on are missing. Forms of degree 2 times 1 plus 1 will be missing. I mean, let me, this needs a little bit of argument with this sort of polynomials. It's not difficult, but let me just give you the first thing. So what is the first term here, right? So if you just expand determinant of 1 plus R over 2 pi, you're going to get 1 plus sum, for the first term, you have sum of omega I. You know, I mean, of course, there is 1 over 2 pi term here, right? There's 1 over 2 pi term here, and this is sums of omega I. Now, sums of omega I, well, all omega I is actually 0, right? So that's equal to 0. So this was supposed to be the term that would give us the term of degree 2, which is missing. So there's nothing there. And there is no term of degree 3 by general reason. So starts here. That's the first Pontryagin class. Now you have to show that the terms of degree 6 are missing. There's no degree 5. Degree 6, you can just write this in terms of Chern roots now. So what would be in terms of Chern roots? I mean, in terms of degree 6 corresponds this sum. I mean, you just first, okay, sum of xi, xj, xk. This sort of I different from j, different from k, right? This sort of elementary symmetric function. But this you can write it as sum of xi to the power 3 minus 3 times sum of xi squared xj, I different from j, and then I would say minus sums of xi cubed. So if you look at this term, this would be trace of a cubed. Now you want to trace, apply trace on both sides, right? So trace of this guy is 0, so its cube is 0. So you have to show that trace of this term is 0, using the fact that trace of sum is 0. Now, why this trace is 0? So trace of sum xi cubed, why this trace is equal to 0? Can you tell me why this trace has to be 0? Well, what is this term? This is trace of a cubed. I mean, or r cubed. Right? This is trace of r cubed. Now, why trace of r cubed is 0? Well, the trace of r cubed is equal to 0 since r cubed itself is a skew symmetric. You see, what is r cubed transpose? Well, I mean, this is just, what is r cubed transpose? This is minus r cubed, I think. The fact that this is an odd term is important here. So its trace is 0. Things like that. So you just argue like that. Now let me give you this as an exercise. This would be nice to try. This is pure algebra. And in fact, it's just pure undergraduate algebra. This is totally in your territory and even below your territory exercise. What is interesting, prove the claim in general. Okay. So now we have got these Pontryagin classes. Now these Pontryagin classes are also integral. They are like Chern classes. In fact, they are closely related to Chern classes. Let me tell you. So I of E are integral. So belong to H for I. Theorem of n are integral classes. In fact, this follows from integrality of Chern classes. Follows from integrality of Chern classes. Plus the following argument that I'm going to give you. I mean, in fact, the claim is that Pontryagin classes are actually nothing but Chern classes of complexified vector bundles. Okay, so P of Pi of E is equal to Ci of okay, so I would say here C to I. C to I of E tensor C. So this is a very important. Well, now let me introduce the notation. E tensor C is this complexification of real vector bundle. So this is the complexification. Of E. Okay. So, and we know that Ci belongs to integral for I cohomology group. But this integral, so this, if we prove this, this easily follows. But you may wonder why you cannot take, say, C2I plus 1 of E tensor C. Well, you can. But the thing is, by the same argument that I showed, this is actually 0 if your vector bundle is the complexification of a real vector bundle. Okay, so what we learn now? So we learn that not every complex vector bundle is a complexification of a real vector bundle. Okay, so let me write it down here because that's a very interesting observation. It shows the difference between global and local linear algebra statements. So if you believe in this, the corollary is that not all complex vector bundles are complexifications of a real vector bundle. That's interesting. Okay, so in fact, for this, it suffices to show the existence of complex vector bundle whose C1 is different from 0. So suffices, in fact, to choose a complex vector bundle F such that C1 of F is different from 0. There are many of those. And then F cannot be written as E tensor K, C, for some real vector bundle E, because because we know that C1 of E tensor C is 0, but C1 of F is not 0. So this is another application of characteristic classes. Now, if you think about it, if you have a complex vector space, so you should compare this with linear algebra. Compare with linear algebra. If you have a complex vector space, F, okay, you can always write it as, not in a canonical way, of course, but can always write it as F equal to E tensor C. So for a real vector vector space. So that's you can do that easily. Just pick a basis here, and then you define your real vector space inside F, and then its complexification is F. So you can do these sort of things, but you notice that I chose a basis to do it. And the moment you choose a basis to prove a statement in linear algebra, you're almost sure that that argument doesn't go through vector bundles. And here is an example of that phenomenon. So this is good thing to think about it. So I think I should just stop and take a break. Okay. So now we need a couple of more classes. We're getting closer to index theory. So yeah. Another definition. Let E to M be a real vector bundle. A hat class, a roof class of E is, you just define it, a roof E is equal to determinant of, so R over 4 pi divided by sine hyperbolic of R over 4 pi square root. Yeah, that's right. Okay, so what does this mean? Well, I mean, let me just tell you, there is this function here, like the Todd class, there was a function. Here there is another function which is like x over sinh of x, right? Sine hyperbolic of x. If you look at this function, let's call it f of x. This function is actually analytic in the neighborhood of 0. Am I right? I mean, this function is analytic. I mean, f of 0 is equal to 0. I mean, is equal to 1. Sorry, just equal to 1. And that is analytic. From here, it follows that there exists unique kind of analytic function. G of x around 0, such that g of 0 is equal to 1 and is actually the root of this function. G of x squared is equal to f of x. Right? So this function, we call it, let x over sine hyperbolic of x, you know, 1/2, by definition, it is formal power series g of x. So it can be defined g of x. Let it be this formal power series. And okay, so here, so this is really like, so a hat of E in this class is like defined to be determinant of this series of, I mean, matrices. Is determinant of the following matrix, which is G of R over 4 pi. Right? R over 4 pi. Notice this is 4 pi. This is not 2 pi. That's important. There's a square root here. So it's related to spin. Okay, so now here, of course, we know that forms that are defined as determinant of f of r or trace of f of r is closed, right? So this follows that, of course, this guy, a hat of E, is closed. We argued, I gave you a general argument, maybe it's in one of the exercises also, to check, because for trace of f of r to be closed follows easily, and this you can derive using that trace fact. Okay, so this is a closed even form. I mean, it's not homogeneous, right? Even, non-homogeneous, homogeneous, maybe, form. Okay, so this is the a roof genus of this vector bundle. Now, a nice exercise here is to actually calculate this function g of x. This is again easy, but it's good to do. Calculate the first non-zero 3 terms of g of x. Okay, and this is to get the following thing and show that this a roof genus is actually 1 minus the first Pontryagin class, I believe. Yes, over 24. 1 over 24, P1 of E. It can be completely expressed in terms of Pontryagin classes. But this I want you to observe from what we know about Pontryagin classes in terms of determinants of yeah. Okay. So this is end of this exercise. But the thing is that in general, this A hat of E is expressible in terms of Pontryagin classes. And we will see that in order to write down the right-hand side of the index theorem for Dirac operators, we need this term, this A hat class, and we have to integrate the A hat class. So find something else, but essentially, this is the main thing. Okay. So another thing is by this thing, so this fact implies that since these Pontryagin classes are integral, classes, the A hat genus is actually a rational class because you're dividing. A hat of E is a rational class. And I will tell you a little bit why this is called, it's actually called a hat genus. Sorry, this is called a hat genus. And I will tell you why this is called a genus, because there is a general notion of genus. Okay, before doing that, let me just get to another class, which is Hirzebruch L genus. That's also we need. Okay, so this is again working. Yeah. Question?
Yeah, so is this somehow, this determinant, is it somehow related to Pfaffian? Because I'm just trying to understand what is going on.
Oh, that's fine. Yes, yes. Yeah, Pfaffian will come, but this one is not. I mean, Pfaffian, I mean, it will come in.
It's also like there is a polynomial such that the square is another polynomial.
Yeah, Pfaffian also you have to take square root of. I mean, you have to take square root of determinant. That's right. But in this case, it's not Pfaffian. It's really just determinant. But it's really just determinant itself that we are taking its square root as element of the ring. But Pfaffian will come soon. Yeah. But when we discuss Euler class, we need Pfaffian indeed. Yeah. And also for Gauss-Bonnet, we need Pfaffian. This was yes, good comment.
Could I ask a question as well?
Yes.
I don't understand necessarily why we have to use certain functions for complex vector bundles and certain ones for real vector bundles. Like the Todd class was defined for complex vector bundles, had a different function, and now we have this function for real vector bundles. Like, why doesn't it work the other way around, for example?
You can apply these things. I mean, of course, if you want to do this, you have to go into. I mean, in principle, you can do that. There's nothing. But because of symmetry, sometimes you get 0, sometimes is not defined as a complex value, the variable could not be complex. But in principle, there is no big difference. But then you see that because of the argument, like Chern classes, I can apply exactly the same definition to real vector bundles. Then I get Pontryagin classes if I work with. So these things goes through. There's no general obstruction. Yeah. But I was thinking you are asking why this sort of functions are these strange, very peculiar functions are used, and there is a good reason for that. So I will explain that.
Okay, thanks.
Okay, not a problem. Okay, very good. So let me now go to this. We need two more classes, and we are through. I mean, for now at least. So this is Hirzebruch L-class. Right. Yes, so Hirzebruch L-class, L polynomial, so to speak. So this time, I don't know what notation is used. Maybe just L of m is equal to determinant of this time. R over 2 pi over tangent hyperbolic of R over 2 pi. But again, square root. So square root. So in this case, again, so this belongs to H even and Duran is a sum of even forms. So in this case, you have to notice this function x over tangent hyperbolic of x. If you call it f of x, this again f of 0 is equal to 1. So there exists unique square root g of x, which is actually analytic, but I just need it to be in formal power series, not more than that, such that g of x squared is equal to f of x. You take root like that. And then, of course, L of m is just determinant of really this g of r over 2 pi. And that's what we mean by that expression. So it's a closed, non-homogeneous even form. Right. And you can integrate this for for E, for example, equal to tangent bundle of m. Then you can integrate this L of m over m, and you get these L numbers. So these are examples of characteristic numbers now. These are L numbers. These are just in general rational numbers. So here is again nice elementary exercise, but it's good. Elementary, I want you to compute this g of x. So actually g of x is equal to 1 plus sum k from 1 to infinity minus 1 to the power k minus 1, 2 to the power 2k over 2k factorial times bk x2k. Okay, so these are of course Bernoulli numbers that they appear in Todd class definition, and they are here. And so show you can derive from this by substituting. You show that L of why did I put L of? It should be L of E. I'm sorry. This is L of E. This is for any vector bundle, a real vector bundle, for example. So show that L of actually E is equal to 1 plus 1/3 of Pontryagin class of E. And remember, we had this formula for a hat. You were supposed to show that a hat of E is equal to 1 minus 1 over 24. Remember 1 over 24 P1 of E, I suppose? Yeah. So you can compare these two things. So here's so if dimension of n is equal to 4 and E is equal to Tm, you can conclude that the A roof of n, Tm, the A roof genus is equal to a minus 8 times the Pontryagin class. No, that's the other way. Sorry. So L of n, we conclude that L of n, L of Tm. So we usually denote it by L of n. I guess I did not introduce a contradictory notation, L of Tm here. This number, integral of L of T. So it's denoted by L of n. That's equal to minus 8 a hat of n. Okay. So what? I'm not sure what I can conclude. So when we prove Atiyah-Singer Index Theorem, Atiyah-Singer Index Theorem, we'll soon prove that. Actually implies that for spin manifolds, a hat of n is equal to index of an operator, which is going to be the Dirac operator for this spin manifold. So because the index is an integer, so this is going to be an integer, right? So it belongs to Z. It's an integer. In general, if the manifold is not a spin, we don't have the Dirac operator and we don't have this index theorem, so we don't know if this is integer. But if it is spin, this is an integer, so L of n is actually a multiple of 8. It's divisible by 8. So that's so this the value of L class is divisible by L number is divisible by 8. So that's significant. Yeah. Yes. Well, by the way, when you integrate, you don't. You see, let me. So notation is a bit is a bit imprecise. Maybe not so imprecise, but I'm not very happy with the notation. But you see, when you integrate this, this is really nothing but because this, like here, this one you don't integrate. You just integrate this part, as by definition is equal to integral of 1/3 of P1 of E. The same with a roof genus. Then you're just integrating the top part. You're not integrating down part because you cannot integrate that. So this is beware of that. Otherwise, then this one is a drop from two sides of the equations, and you're comparing these things. So I will come to this soon. Okay, now. About Pfaffian, so let me now tell you how Pfaffian appear. Any questions about this? Okay, very good. Now let me just so far, let me see what we have achieved so far. So far, Basically, we use two methods to define these characteristic classes and characteristic numbers. One method was trace of f of r, right? Trace method, and the other one was determinant method. And this was very, very easy and universal, actually, for any formal power series in R of x or C of x. This work in general. So this is a very general, we have these two methods. But there is another method which is quite relevant for the story of characteristic classes. This is the method of invariant polynomials. So this is third method, invariant polynomials. So let me tell you what the story is in this case. So in general, again, this is purely algebraic question now. So let G be any Lie group. Any Lie group. Let this G be Lie algebra of G. Now, this group G acts on Lie algebra by conjugation, by adjoint map. So this is called add the G to automorphisms of G. So this is automorphisms of this guy. This is a group. This is Lie algebra automorphisms. Okay. So this is a group of Lie algebra autos. By Lie algebra automorphism, I mean map like T from G to G. This is 1, 1 onto linear and preserves the bracket operation Tx Ty is equal to T bracket Xy, right? So this is kind of natural group you attach to any structure. This is a group of structure preserving morphisms of your theory. So this is a group. This is a group. So it's a group homomorphism. So let me give you an example of this so that you can see that this is something you already know from linear algebra. So let me give you an example. The example of this is G equal to GLN R. And then it's Lie algebra. You can easily see that in Lie algebra of this is actually n by n matrices. So that's a very easy, familiar Lie algebra, you know. And what is this add? So add of G on A is just conjugation. So this is the adjoint action or conjugation action, right? So this is a well-known thing from linear algebra. So for any G belonging to GLN, and for any A, of course, belonging to M, right? You can do the similar thing for GLNC. I mean, if G is GLNC, then its Lie algebra is, of course, n by n complex matrices. These are easy, and you have the same thing. Now, what is invariant polynomial? So there's a very general definition. So let me define. So definition, invariant polynomial maps. I mean, I'm referring to this general construction. Is a map from P, from Lie algebra to R or C, such that P is a polynomial map. I mean, defining a polynomial map is not a problem, right? For any vector space, you can define what is a polynomial map on that vector space. You pick a basis, And in that basis, your vector space is isomorphic to Rn or Cn or Fn. And then this is just a polynomial function n variable. And that concept is independent of choice of basis. We can easily see that, okay? So this is a polynomial map. But the crucial property of this polynomial map is that P of at G of X is equal to P of X for all G in your Lie group and for all X in your Lie algebra. So in particular, in this case, if you have this, so we are looking for maps from Nn of R, for example, and by n matrices to R, such that P of G A, well, let me call it X, in conformity with this notation, maybe X. X G inverse is equal to P of X, right? So this is this crucial property. So now this is a ring, of course, you see, I mean, so let me tell you, it's a commutative ring. So it's usually called G in E. This is the commutative ring of invariant polynomial. Invariant polys G. So of course this is a subring of the ring of all polynomial functions of G, which is polynomial functions in n variable where n is the dimension of G, right? So this is subring of all polynomial maps, polymaps on G. Now the first question is to classify this ring. What is this ring? So this is an interesting problem in linear algebra, Lie theory, basic Lie theory stuff. You want to know what is the structure of this ring. Remember, we had a similar problem for symmetric functions. For example, what is the structure of all symmetric functions or symmetric polynomials in n variables? These two questions are actually related. So in this case, so e.g. for G, I mean equal to Nn of R, and G equal to GLN R. Okay, so first of all, let's see if we know some functions here. So what kind of functions we know, right? That are, what kind of polynomial functions we can describe that is invariant in this sense? Give me some functions, some polynomials. Start with the simplest, for example.
Constant polynomials?
Yeah, absolutely. Yeah. Oh, fine. Constant polynomial. These are polynomials of degree 0. Good. Yes. What else? Next one.
Trace.
Trace. Yes. So 1 trace of x. X is here, right? Is an n by n matrix. What else?
Determinants?
Determinant of x, yes. Obviously, determinant is satisfied. What else? I give $1 to correct answer now.
Is the Pfaffian one?
Pfaffian is not yet here. We cannot define Pfaffian in this generality. Yeah, but it's a good guess. Yeah, but it's not there yet. We are not there yet. You need to restrict the type of matrices you're looking for. But there are simpler, much simpler things than Pfaffians. What about trace of x2? Right? You see, amazingly, G inverse 2 is equal to G x2 G inverse. So trace is, because of this peculiar property of conjugation, this is just that, right? And then you can go on, trace of x cubed. And then you can just stop at trace of x. Now you can prove the following lemma easily. That any invariant polynomial on GLN which is N of R, is a polynomial in these functions. Of course, one is a constant term. We don't trace of x, trace of x2, trace of xn. Right? And in fact, in a unique way. I mean, proving this lemma is not difficult. You just have to know what you're doing. I can give you the idea of proof, but let me just. But there was an answer in terms of determinant. So the question now the claim is that determinant can also be written in terms of these things. So determinant of x can be written in terms of 1 trace of x, trace of x2, trace of x3, and so on and so forth. And 1. Of course you can, right? Because if you think about it, we have this beautiful formula, determinant of 1 plus r is equal to 1 plus trace of r plus trace of r2. I don't know what I'm doing here, but I hope it's okay, plus so on. Okay, so anyhow, so I will give the determinant as an exercise. But before, okay, so let me just say how to prove it in a second. But let me just GLN R invariant is isomorphic to R of polynomial ring in n variables, x1, xn. Well, this is like trace, this is like trace of x2, and this is like trace of xn. We can do similarly for GLNC, the same proof goes. Invariant polynomials is isomorphic to C. Okay, so this is good. And this is the theory of Chern-classes, basically, in this. Okay, so now let me explain now why we need. So what is the relation? So before, what is the relation with characteristic classes? I mean, that's our motivation, right? That's why we care about this thing. Yeah.
Do you, in general, have that the polynomial maps on Lie algebra is the whole polynomial ring, or?
No.
No.
No. In general, for general Lie algebra, it's a very complicated ring to describe. It uses a lot of structure of Lie algebra. I believe it can be expressed in terms of roots and this sort of data, combinatorial data for Lie algebra. But for simple Lie algebras like this, it can be expressed in terms of just polynomials. And for also for SO2n, it's also a polynomial, but that is, we have to add one more variable, and that variable is just Pfaffian. So we'll see that soon.
Okay.
Yeah, that's right. Okay, so now relation, but before explaining Pfaffian, let me just relation with characteristic classes. What is the relation? Well, the point is that for any polynomial p belonging to G, I mean, let me just be down to earth and take Mn of R instead of generally to Mn of R invariant. You can construct a characteristic class C. A characteristic class. Now, this looks very strange. So how can we just use this pure algebra issues to construct a characteristic class now? Well, the reason is this. We can just apply P. The characteristic class is this P applied to this matrix R. And you take its class. This is the characteristic class defined. Characteristic class defined by P. Polynomial P. P belonging to Mn of R invariant. Right? So now, two questions you have to worry about. Why is this a well-defined concept? Because what if you choose a different connection? And what if you choose a different frame? There are two issues here. But issue one, since changing a frame or changing frames gives R prime something like G R G inverse. Because you see, if you change your frames, you'll get a different matrix of two forms, right? But there is a very beautiful relation between these two things. It's of this form, R prime is equal to G R G inverse, where, you know, this matrix R, of course, is IJ, matrix of two forms, remember? R prime is equal to R prime IJ. Totally different forms, but G is a matrix that at each point is just an invertible matrix, right? Belong to GLN. I mean, G of X, let me call it, belong to GLN R for every X belonging to that coordinate patch, U alpha. And you're working locally by choosing a coordinate system here and choosing a frame, right? And now choosing a frame, like a different frame, like EI prime, it is a different frame, and original frame like EI, but these things are related by each other through this matrix. So at each point, you have one basis and you have another basis, so they are related by an invertible map, right? So this EI prime is equal to G EI. I mean, I'm now using a kind of very collectively, I write E prime is equal to GE. So if you want, you can write here like E1 prime, En prime is a column where each entry of the column is one of the frame members. This is like G times E1. You see, if you think about things you learn in linear algebra, the change of basis from one basis to another basis is always like this, right? And this matrix changes from point to point, so you get this matrix G of X in general, but then R prime is equal to this. Okay, so now you see the point of invariant polynomials. It doesn't change. You get the same form, right? So this is the beauty of this construction, first of all. P of R prime is equal to P of R. Okay. Now, the second thing is that, of course, you have to show that this is independent of choice of connection, which you can, as before. I mean, Okay, so this is a very general method now to construct yet another method to construct characteristic classes. In other words, you study the invariant polynomials on your Lie algebra, and any invariant polynomial gives you a characteristic class. So basically, you construct a map from G, from G invariant to, basically cohomology ring. You get a class on cohomology. Maybe you haven't seen this notation, but people usually put a star. It means that it's a direct sum of all these things. And this is actually a ring map. We have to fix this bundle E over N, and we have to assume that the curvature matrix takes values in this Lie algebra G, which, okay, so, we are working only so far with G equal to GLN and GLNC, in the complex case GLNC. And secretly also, we have been working in the case of UN and in the case of SON as well, at least ON as well. Okay, so this is the original Chern-Weil construction, really. Now, so I think it's we better stop right now and discuss, because time is, we discuss this Pfaffian and these things for the next time. And that's the end of the our quick, rapid discussion of characteristic classes. So Pfaffians, so let me just tell you where Pfaffians come from. So Pfaffian comes from when you want to look at invariant, you see SON, SO2N, invariant. You want to study, so what is this first of all? These are matrices such that, first of all, they are skew symmetric, even, and this little s, it doesn't matter even, because in this case, it's just, it's the connected component of the two Lie groups, O2N and SO2N are the same, so the Lie algebras are the same, so there's no difference really, but I may put it here. So this is just these ones. So this is a skew symmetric. Two n by 2n matrices, right? 2n by 2n, say real or complex, it doesn't matter, but here is real, for example, real matrix. And now the question is, what is this? Right? So the question is, what is this? Of course, we have the old invariant polynomials, right? Trace of x, trace of x2, trace of xn. Or we have the same as before. Of course, there's one, but then trace of x, trace of x2, trace of xn. Where, I would say in this case trace of x2n, sorry. Yeah. But now the question is it all of those? Is that it? Have we exhausted all possibilities in terms of traces? And the question is that no, there is one more polynomial map. So this is called Pfaffian. So there is a polynomial map Pfaffian from this O2N to R. And its crucial property is that Pfaffian of x squared is equal to determinant of x. It's just the square root of the determinant. But the amazing thing is that it's a polynomial map. If you think about it, this is quite remarkable, because if you look at determinant, for example, as a function of the entries of the matrix, it's a very complicated polynomial in n squared variables. In this case, it's less because the matrix is skew symmetric, right? So we have that. But now this is amazingly is going to be square of a polynomial. And that polynomial is actually integer with integer coefficients. You don't have to go beyond rings to define this. You see, the determinant is a polynomial with plus minus 1 coefficients. So. And this one is also only a polynomial with plus minus 1 coefficients. So that's really an amazing thing. But now let us check the 2 by 2 case. That's very easy, of course, in that case, because I mean the matrix, because it's a skew symmetric, and so it's 0, A minus A, 0, and the determinant of this is equal to A2. Of course, is equal to Pfaffian of A squared. You declare Pfaffian to be this. So determinant has degree 2n, but Pfaffian must have degree n. Pfaffian has degree n. Now, just go to, well, there's no claim about, I mean, determinant of 3 by 3 skew symmetric matrix is 0, right? If x transpose plus x is equal to 0 and n is equal to r. That's the kind of exercises we like to torture undergraduates with, right? And then determinant of, so there's nothing about 3 by 3. Now go to 4 by 4. You get 0, A, B, C, minus A, 0, D, E. Here is again what to put, minus B. I put minus C here, then minus D, 0, F. And here is, oh my God, what I did, I don't know. Minus E, and then minus F. I think it's 0. Is that okay? Yeah, I think it's okay. Right. So it's a polynomial in how many variables? 1, 2, 3, 4, 5, 6 variables. You have to, of degree 6, you have to write it as square of a polynomial of degree 3 in variables A, B, C, D, E. Try to find this A. I mean, Pfaffian of A in this case. It's not trivial. I mean, this is just 4 by 4. And then try to do 2n by 2n. So that's a big fish to fry, right? In that case. So, yeah, but this was apparently done for some reason. I don't know what was the motivation by Pfaff. Pfaff was a mathematician, I think at the time of Gauss. So someone asked, what is the greatest mathematician in Germany? The answer came out to be, they were discussing, the guy said it's Pfaff. And then the other guy asked, what about Gauss? And he said, well, of course, Gauss is the greatest mathematician of the whole world, not Germany. So this was the, so Pfaff was a great mathematician indeed. Okay, guys, I should stop on this point.